A supply chain is a linked series of nodes: suppliers, manufacturers, distribution centers, retailers, and finally customers. Material flow is the physical movement of goods from raw material source to end user. Think of a river carrying water downstream. Information flow travels in the opposite direction. Customers send demand signals, retailers send sales data, manufacturers share production plans. Coordination mechanisms are the rules or contracts that make the nodes work together, such as push versus pull systems, contracts, or shared IT platforms. Real-world analogy: imagine a relay race. Each runner node must receive the baton material and the race strategy information at the right time. The coach's instructions, coordination ensure the team finishes fast. Accurate demand forecasts keep order quantities stable. Two classic simple methods are: moving average, MA, dash the forecast for period T plus 1 is the average of the last n observed demands. D hat sub T plus 1 equals 1 over n times the sum from I equals 0 to n minus 1 of D sub T minus I. It smooths random spikes but lags behind trends. Exponential smoothing ease dash weights recent observations more heavily. D hat sub T plus 1 equals alpha D sub T plus 1 minus alpha times D hat sub T, where 0 less than alpha less than or equal to 1. A larger alpha reacts quickly, a smaller one smooths more. Impact on order batches. If a forecast suddenly jumps because of a one-off spike, the buying department may place a large order batch to avoid stock outs. Reordering based on noisy forecasts creates variability in order sizes, which is the first step toward the bullwhip effect. Example: a retailer using a 3-month moving average sees demand of 100, 120, 140 units. 100 plus 120 plus 140 divided by 3 equals 120 units. Even though the actual demand trend is upward, leading to an under-order and later a bigger emergency order. The bullwhip effect is the phenomenon where the variance or amplification of orders increases as we move upstream in the supply chain. Formally, if sigma D squared is the variance of end customer demand, and sigma O squared is the variance of orders placed by a downstream node, the amplification ratio is amplification equals sigma O squared divided by sigma D squared. A simple analytical model, Lee Padmanabhan and Wang 1997, shows that for a linear order up to base stock policy with lead time L and forecast error variance sigma F squared, sigma O squared equals sigma D squared times the quantity 1 plus L squared times sigma F squared divided by sigma D squared. Numerical examples. Customer demand, mean 100 units per week, variance sigma D squared equals 20 squared, which is 400. Forecast error standard deviation sigma F equals 15, variance 225. Lead time L equals 3 weeks. Then, sigma O squared equals 400 times the quantity 1 plus 3 squared times 225 divided by 400 equals 400 times the quantity 1 plus 9 times 0.5625 equals 400 times 6.0625, which is 2,425. Amplification ratio equals 2,425 divided by 400, approximately 6.06. Orders are 6 times more volatile than actual sales. This illustrates why a small forecasting error magnified by lead time can cause large swings upstream. Different inventory policies shape how much order variability is passed upstream. Economic order quantity, EOQ classic batch, size model minimizing total cost, ordering plus holding. Q star equals square root of 2ds over 8. Where D equals annual demand, S equals ordering cost per order, H equals holding cost per unit per year. A large Q star creates big order batches which can amplify the bullwhip if demand is erratic. SQ policy combines a reorder point S trigger and a fixed order quantity Q. S equals mu L plus Z sigma L, where mu L and sigma L are mean and standard deviation of demand during lead time. Z is the service level factor. When demand exceeds S, a full Q is ordered, creating a sawtooth inventory pattern. Sigma O squared equals Q squared over 12 plus sigma D squared. Approximation assuming demand normal and independent. Larger Q directly raises variance. Periodic review RS model inventory is reviewed every R periods. An order is placed to raise the inventory position to target S. Order T equals S minus IPT, where IPT is the inventory position at review. The order variance depends on R longer review periods increase the chance of multiple demand spikes, accumulating thus higher sigma O squared. Sigma O squared equals sigma D squared times R plus S minus mu R squared over 12, where mu R is expected demand over R. By choosing small r continuous review, the firm can dampen the bullwhip. In summary, policies that use large fixed batch sizes or long review intervals tend to magnify order variance, feeding the bullwhip. Explanation: sharing accurate information across the chain can dramatically cut the amplification. 3 common collaborative tools are: Number 1, Vendor Managed Inventory, VMI. The supplier monitors the retailer's inventory, often via electronic data interchange, and decides when to replenish. The retailer's order variability is replaced by the supplier's replenishment rule, usually a smoother base stock policy. C total equals C inv plus C order plus C stockout minus BVMI, where BVMI captures savings from reduced safety stock and fewer emergency orders. Number 2, Collaborative Planning, Forecasting and Replenishment. CPFR partners jointly develop forecasts and share promotion plans. Sigma F call squared equals 1 minus rho times sigma F squared, where rho is the correlation, 0 less than or equal to rho less than or equal to 1 of the shared information. Higher rho means better alignment and lower error, thus lower order variance. Number 3, Collaborative Forecasting, CF. Each node shares its point of sale data. The upstream node uses a weighted average. D hat T superscript CF equals W D hat T superscript downstream plus open parenthesis 1 minus W close parenthesis D hat T superscript internal. Choosing weight W close to 1 gives more trust to downstream data, decreasing the forecast error term sigma F in the amplification formula. Overall benefit: when demand information is transmitted instantly, low lead time, and accurately, low sigma F, the term L squared sigma F squared divided by sigma D squared in the bullwhip variance formula shrinks, meaning far less amplification. These strategies often require investment in IT, ERP, cloud platforms, and contractual trust, which appear as the B term above. The benefit must outweigh the implementation cost. Lead time variability and safety stock directly influence order volatility. Safety stock formula, service level based. SS equals Z sigma DL, where Z is the Z score for desired fill rate, for example 1.65 for 95% service, and sigma DL is the standard deviation of demand during lead time. Sigma DL equals square root of open parenthesis L sigma D squared plus sigma L squared mu D squared close parenthesis. Here sigma L captures lead time variability. A larger sigma L drives up safety stock, increasing holding cost and the size of each replenishment order, which in turn raises the order variance. Lead time variance analysis. Suppose demand is steady, sigma D equals 0, but lead time varies. Then sigma DL equals mu D sigma L. If lead time doubles its standard deviation, safety stock doubles, causing larger and more erratic orders, a pure lead time-induced bullwhip. Mitigation techniques. Shortening and stabilizing lead time, for example local sourcing, better carrier contracts, reduces sigma L and therefore SS. Dynamic safety stock. Recompute SS each review period using latest lead time data rather than a fixed buffer. Decoupling points. Locate inventory strategically, for example at regional distribution centers, to isolate downstream lead time variability from upstream suppliers. By controlling both the mean and variance of lead time, firms can keep safety stock levels modest and avoid feeding excess variability into the supply chain. Performance in a supply chain is measured by a mix of service and cost metrics. The most common ones are: service level alpha is the probability that demand is met from on-hand inventory. Mathematically, alpha equals 1 minus expected stockout divided by D. Fill rate beta is the fraction of total demand units satisfied immediately. often expressed as beta equals 1 minus backordered units divided by total demand. Total cost TC is the sum of ordering, holding, and stockout costs. TC equals D divided by Q times S plus Q divided by 2 times H plus C stockout. C stockout equals P times expected backorder, with P the penalty per unit. Trade-off: raising service level, larger safety stock, lowers stockout cost but raises holding cost. The optimal point can be found by minimizing total cost subject to a target alpha or beta. The classic news vendor model provides a closed-form solution for a single period setting. Q star equals F inverse of P over P plus H, where F inverse is the inverse demand cumulative distribution function. Multi-period optimization often uses a linear program. Minimize the sum over I of Si times Xi plus Hi times II plus Pi times Bi, subject to inventory balance constraints. I sub I minus 1 plus Xi minus Di equals II plus Bi. The model shows how a decision to increase order frequency, smaller Xi, can cut holding cost but raise ordering cost, while a higher safety stock level reduces Bi backorders. In the context of Bullwhip, a company that pursues very high service levels at each echelon often inflates safety stock, which propagates large order swings upstream, a classic cost-service trade-off. Explanation: sample exam-ready questions. 1 period calculation -EOQ and safety stock. A retailer faces an annual demand of 12,000 units. Ordering cost is $50 per order, holding cost is $2 per unit per year. Lead time is 2 weeks with a standard deviation of 0.5 weeks. Desired service level is 95%, Z equals 1.65. Calculate A EOQ Q star B safety stock SS, C total annual cost, ordering plus holding plus safety stock cost. Answer sketch : convert demand to weekly 12,000 divided by 52 approximately equals 231 units per week. EOQ Q star equals square root of open parentheses 2ds divided by H close parentheses equals square root of open parentheses 2 times 12,000 times 50 divided by 2 close parentheses, approximately equals 775 units. Demand during lead time mean equals 231 times 2 equals 462 units. Sigma DL equals square root of open parentheses L sigma D squared plus sigma L squared mu D squared close parentheses, approximately equals square root of open parentheses 2 times 231 squared times 0.5 squared plus 0.5 squared times 230, 1 squared close parentheses, approximately equals 260 units. SS equals 1.65 times 260, approximately equals 429 units. Holding cost equals open parentheses Q divided by 2 plus SS close parentheses. H equals open parentheses 775 divided by 2 plus 429 close parentheses times 2 approximately equals $2,398. Ordering cost equals open parentheses D divided by Q close parentheses. S equals open parentheses 12,000 divided by 775 close parentheses times 50 approximately equals $774. Total approximately equals $3,172. 2-period conceptual MCQ. Which of the following most directly reduces the bullwhip amplification ratio? A. Increasing order batch size. B. Extending supplier lead time. C. Sharing point of sale data with upstream partners. D. Raising safety stock at each echelon. Correct answer: C. Accurate downstream demand information lowers forecast error sigma F in the amplification formula. 3-period numerical bullwhip illustration. Customer demand variance is 400. Forecast error variance is 225. Lead time is 4 weeks. Compute the order variance and the amplification factor. Sigma O squared equals sigma D squared open parentheses 1 plus L squared sigma F squared divided by sigma D squared close parentheses. Sigma O squared equals 400 open bracket 1 plus 4 squared times 225 divided by 400 close bracket equals 400 open bracket 1 plus 16 times 0.5625 close bracket equals 400 open bracket 1 plus 9 close bracket equals 4,000. Amplification equals 4,000 divided by 400 equals 10. Interpretation: orders are 10 times more volatile than sales. For period true or false. Periodic review inventory systems always generate higher order variance than continuous review open parentheses, S, Q close parentheses systems. Answer true, because longer review periods allow demand to accumulate, increasing sigma O squared. These questions test both quantitative skills, EOQ, safety stock calculations, variance formulas, and conceptual